So what I'll do is I'll tackle, let's do B, I guess, with, so this is page 4 again, with linearization first, and then after that we'll use Newton's method. All right. So the linearization approach just requires you to kind of deconstruct what you're given and put it in function form. So you're looking at, instead of the cube root of 7, you would want to have it as f of x is equal to the cube root of x, where x is equal to 7. All right. So using linearization, so I'll make a note of that. Linearization and linear approximation mean the same thing, right? Both multiple syllables, so it doesn't really matter. Yeah, you're not going to save yourself any energy by calling it one thing as opposed to the other. So what we want to do is choose a convenient value all right, near 7. And convenience is determined based off of the nature of the function. Right? If it's a trig function, we would not choose the same value that we're going to choose for a cube root function or a log function or exponential function or whatever. All right? So in this case, we want to choose, or we want to, and that value would be an a value. So we're going to let the a value be equal to what? 8. All right, that's the cube root that's closest, or I'm sorry, the perfect cube that's closest to 7. All right, so we're going to evaluate our original function for that number. So f of 8, so cube root of 8, which is 2. We also need the derivative, right? So f of x can also be thought of as x to the 1/3. So the derivative of that would be what?
1/3. X to the -2/3.
Exactly. So we want to evaluate that for where x is equal to 8. Now it's up to you if you want to do that in your calculator, in your head, but you do need to come up be prepared to come up with an exact answer. All right, so this is 1/3 times, now that negative exponent is telling me that I'm going to take the reciprocal of whatever I get. So I hang on to that. Whenever I'm dealing with a fractional exponent, I always work bottom to top. So I'm popping in an 8 for x. I need the cube root of 8, which is what?
2.
Power of 2. So
4.
flip it.
So 1/4.
1/4. All right. Since the numbers for this are going to end up being clean anyway, bottom line is I'm not going to know the difference. If you put it in your calculator and then math bracket, you're going to get the 1/12. In the end, what do you get? You get the right answer, which is fine, but at least try to do it, because then you develop a little bit more number sense, and that's probably going to carry you a little bit further in life, you know. So, because I guarantee you're not going to be taking a derivative on a daily basis, but you will have to crunch some numbers at some point. All right. So L of x will be equal to 2 plus 1/12 times x minus our convenient value of 8. Now if I want to determine what the cube root of 7 is, I'm going to pop in the 7 for x. And really, that last line in black, L of x equals, that's really all the first question on the exit ticket was asking you to do. Just come up with a linear approximation model. If you had to do the second question, you would have had to go, you would have started over, but you would have had to go a little bit further. Right? And that would be corresponding with this approach. So this is the same as 2 minus 1/12. Which is the same as 1 and 11/12. All right. Now, I know that the cube root of 8, and so do you, is equal to 2. 7 is a little bit smaller than 8, So its cube root should be a little bit smaller than 2. And 1 and 11/12 is a little bit smaller, so I'm feeling pretty good about that. All right. So that's the linearization approach. Now what we want to do is get the solution using Newton's method. For Newton's method, what we want to do is we want to write a function that will have a solution equal to whatever the value is that we're trying to evaluate. So we know that our x value, x should be equal to the cube root of 7. Excellent. So for the sake of cleaning it up, what I'm going to do is I'm going to cube both sides. And that's going to give me x cubed equals 7. But Newton's method helps us find the zeros of a function, or the roots. So basically where the function is equal to 0. So I'm gonna manufacture that. All right, I'm gonna subtract the 7 from both sides and get x cubed minus 7 is equal to 0. All right. Now when you're working through these problems, you'll see on the answer key that I did a lot of extra work because I did a lot of them by hand, just to show you how it works. You don't need to do it by hand. You do it on the calculator. So what we do is we run the Newton's method program, Newt, and all you have to do is state your initial guess. All right. The number of iterations. And your solutions. Because there could be more than one. All right, but since we're only looking for one particular value, the cube root of 7, we're pretty confident that once we get it, we'll know it. All right, because we know it's going to be some value that's a little bit less than 1. All right, so go to our calculators. I don't even know who the calculator is. All right, so you're going to run the program Newt. Assuming that TP wants to turn that. Did I miss? I might have missed. I'm going to type in my x cubed minus 7. Let's say I have no idea what the answer is, but I do know it's going to be positive. So I'll pop in a 10 as my initial guess.
Yeah, how do you get?
It's actually called guess because it really is a guess.
Then why do they even want? Why does it even include if it doesn't?
Because you need to give the algorithm someplace to start. Otherwise, it just won't do anything. So once you give it a place to start, it starts narrowing down the field and working towards the appropriate solution.
How come you put parentheses around the x cubed? Because wouldn't that make it x to the 3 minus 7? Or no?
Order of operations has the powers happening before any other operation, so it would raise the x to the third and then, yeah. So we're good there. So I'm going to hit enter again. That's my second iteration. It's getting closer to the true value. We're not there yet, but we're getting closer. Closer still. Even closer. Better. And eventually it's going to say done if there is a solution.
I used 7.
So once there's no change in consecutive values, then you know that you're done. All right, so we actually had it after the 8th iteration, but the calculator needs to verify that there's no change in value before it gives you a done. So technically, this is an initial guess of 10 with 8 iterations. Now, I'm not going to split hairs over that. If on an assessment you wrote initial guess of 10 and 9 iterations, it's going to be fine. And I'm not taking off for that. The solution would be that last decimal value, depending on how you're requested to round it, I'm just gonna write the whole thing. So 1.912931183.
I have a question for the number of iterations. Can you just do the one before the last one? Is that like a
Yeah.
rule?
Yeah.
That you should do?
That's generally the rule, yeah. All right. So I only have one solution here. I kind of knew that going in because the cube root of 7 is only going to be one finite value. Right? But it is possible that you could have a function that has multiple solutions. All right, so let's take a look at the next page. And this is the last thing we'll do together. Our last idea. Newton's method to solve these two bad boys. So the first thing I'm going to do is take a look at this equation graphically. All right, I don't need to do this stuff. The other classes. All right, so I'm going to type in my x to the fourth. What is it, minus 5x plus 2? 5x plus 2. I'm just going to take a quick look at the pictures in 6. I see that there are two x-intercepts. So that's telling me what my two guesses should be near. All right, so what I'm going to do is I'm going to select a value as my initial guess. I'm going to need two of them. One that's closer to the first intersection and one that's closer to the second intersection. All right, so here I'm going to let, so my first guess, it's going to be, it looks like about a 1, something in the neighborhood of 1. Then for the second one, well, I just don't want it to drag me to the same solution. So it's got to be closer to the second intersection than the first one. Maybe it's 3, but play it safe. Just choose something that you know is definitely to the right of the second intersection. You put 100 if you want. It's just you're going to be hitting enter a lot. Right? I'll put 5. Then we need our iterations. And then we'll have our solutions. All right, so that one looks weird. Put it over here. I should really just bring that over here. All right, so program new. X to the fourth minus 5x plus 2. I'll put in the 1, enter, 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 enter. After the 6th iteration, so it's really the 5th iteration, we get our done. All right, so So 5 iterations, and we're looking at 0.405-ish. That's just to the 3 decimal places, so 0.405. And then for the other solution, just run the program again. You can just hit enter. It automatically runs the last calculation another time, in this case the program. So you just type it in again, x to the fourth, minus 5x plus 2. Pop in my 5. So 9 iterations in about 1.548. So these would be my 2 solutions. All right. And that's really it, because the whole idea behind using Newton's method is to avoid having to do complicated algebra and stuff like that. So, if you find yourself not having to write a lot of stuff down to get answers to these questions, then you're doing it right. Okay? The The only little twist that comes into play is like little applications of it, like in number 6, part A and B, where it says solve the system of equations. You know, what would, if I were to do this algebraically, what would my first move be? If I wanted to solve the system of equations, y equals
Go into
sine.
2 and then take out the x? No. Maybe. Oh, I'm looking at the wrong spot, so disregard that. But that was a good thought for the previous one.
It
It
was.
was spot on.
Spot on. What are some techniques that you could use in order to solve a system of equations? Substitution or elimination.
Cannonball.
All right.
On it today.
So both of these are equal to y. So they're equal to each other. So I could say sine of x equals cosine of x. All right. And so Newton's method requires the whole equation to be equal to 0. So what should I do now?
Sin x minus cosine x.
Sine x minus cosine x equals 1.
Zoomed.
All right. And so really what you get out of this is you can use Newton's method for a system. You're just going to subtract one equation from another. All right. So in the case of part B, I actually think B is harder than A, because B, you'll have to remember to either put parentheses in or distribute a negative. And you'll also have to take a look to see how many solutions there are. All right. In A, you have a restricted domain. It's on 0 to pi. If there are more than one solutions, it would be surprising. Well, more than one solution, it would be surprising, right? But you can still look at the picture, right? So I was originally just going to talk you through this one, but I might as well just do it. So sine of x minus cosine of x. We actually talked about graphing trig functions way back in the beginning of the course, but that's way back in the beginning of the course. Does anybody remember the best way to come up with the graph of a trig function? It's actually a very simple answer.
Plug it in.
Oh yeah.
All right.
So now that we've plugged it in, do I want to just hit graph or should I hit something else?
Second.
Don't you have to change your view and then change the zoom?
Change your view, change your zoom, okay? So let's go into the zoom. Which
Nice, Brianna.
zoom seems
Nice.
most appropriate? Which one?
Zoom trig?
Zoom trig, yeah. All right, so we select zoom trig. I believe I have my derivative function on, so that might give me a straight function. Let me actually turn that off and do it again. Oh, it is off. Oh, look at that. All right. So now, once I have that,
Oh. Gorgeous.
it's great. I'm just gonna have to not answer the questions. So then,
Roasted.
yeah, but you didn't hear that, so it's fine.
He's
So,
ugly.
oh,
Ouch.
that's horrible.
Now you're listening.
Yeah,
Now
but-
you're listening.
He's not.
But
I
he didn't
am.
hear it.
Oh, it was Ian that said ouch?
Yeah. But,
Why does that hurt you, Ian?
but, oh, come on.
No?
Why are you lying, Noah? Like,
Yeah,
don't make a
no,
lie.
okay.
no bueno on that kind of
Luke
stuff.
knows how I feel about him. I just had to get his attention
I
somehow.
know, but anything taken out of context.
Okay, I
No,
take
like,
it back.
it smells funny or something. It's
Luke,
like,
you're gorgeous. Wow.
It's not going.
All right.
He knows I love him.
I was turned it off.
Oh, yeah.
So, once I have my zoom trig, I now account for the window that they gave me, change my x min and x max to 0 to pi, then hit graph, and now I I have the perfect window for the trig function. All right, and the only thing I really need out of this is how many solutions there are going to be. Right, so I now know that using Newton's method, I'm only on the lookout for one solution. So into my program, Newt. Type in your function sine x minus cosine x. It works the other way too, cosine x minus sine x. Take a guess. Well, the guess has to be between 0 and pi, or 0 and 3.14-ish. So you could do it in terms of pi, or you just put twos in the interval. Enter, enter, enter.
Mr. Han, what
This
are those
is
little numbers? Oh
not
wait, never mind.
working.
I take that back. I don't say.
Guys, I got it. 2, 3, 4, 5.
Yeah, like one, the first number.
Sorry that I'm a genius.
I got 6.
You got
Not
6.
really wrong,
Yeah.
it's weirdly
Yeah, you're
long.
talking.
Oh no, I'm asking for more.
Oh, you would be one
Let me try
No,
one.
I'm just gonna shoot.
Okay,
Well, 5, but.
I'll be
He's
annoying.
like, I'm ordering again.
Yeah, it should have been 0.75, 785. So what ended up happening when I selected 2 as my initial value, it dragged me to a value outside the interval. So this is actually a very important concept.
Oh wait, no, I don't have roll name.
I like to know
The guess.
Yeah.
The guess is the
No,
guess
it's
concept.
more like.
The-
So what
the-
should the guess have been?
So once I plugged into 2, it dragged me somewhere that I didn't want to go.
Right.
So I had to adjust for that by reducing it. So
Reducing the value.
reducing my guess. So I brought it down to a 1. If that still dragged me to a place I didn't want to go, then I'd reduce it even further.
Okay.
So the better your guess, so this is 3 iterations, the better your guess, the more likely it is you're going to hit the solution you're looking for, because a periodic function could have infinitely many solutions. And so it could conceivably drag, if you got the 6, then it dragged us to the wrong one.
How do you know that it's wrong?
Because our domain is 0 to pi.
Oh, gotcha.
And so when you go into your graph, just take a good look at where that intersection is. That tick mark there is at 1. So if you wanted to, you could actually just put in a 0.5. It'll pretty much bring you right there. Yeah. Now, I did notice that some folks throughout the lesson opted to just stop listening, and that's fine. Even though there won't be any unit tests, there will be assessments, and there will be plenty of opportunities for you to not succeed in this course moving forward. So I don't do the direct instruction very often, but when I do have the expectation that I would have your undivided attention. So what just happened over the last few minutes, that can't happen moving forward. All right. So you have plenty of time to have your social interactions. It can't happen when I'm doing direct instruction. All right.